Okay, thank you very much. So I hope everybody of you survived the typhoon yesterday. So maybe recall at the end of the last lecture we discussed the Condé index for two-dimensional symplectic matrices. So we have psi from 0, 1 to SL2R smooth, and psi 0 is the identity, and then we can also have psi dot equals J S psi. J is just multiplication by I, and then we have the operator AS W12 S1 R2 to L2 S1 R2. V goes to minus J dTV minus SV, and we associated to the eigenvalues of this operator a winding number. So if eta is an eigenvalue, then we associate it to this V eta set the winding number. This was done. We first associated the winding number to an eigenvector. So eigenvector is just a non-vanishing map to R2. So we normalize. So we have a map from S1 to S1, and we take the degree. And then we showed that it doesn't depend on the choice of the vector. And then using this, and so because this winding number only depends on the eigenvalue, eigenvalues of different winding number cannot cross. And this is, gives us quite nice information about this, how the vectors, eigenvalues and the binding numbers are distributed. So if we have S, we can look at the homotopy from S to 0. So we just look at the homotopy. Rs are in 0, 1, and then for r equals 0, then we can compute explicitly. We have just this operator, and we have always an eigenvalue at the multiples of integer multiples of 2 pi. So, and we have actually, multiplicity is always 2. And then if we start perturbing them, then usually, also maybe they continue to be double 1, this we don't know, but generically 2 come out, and they might cross again, but this family and this family, they never cross, because they have, namely the binding number here. The binding number here is minus 2, here is minus 1, here is 0, here is 1, and here is 2. So these different families cannot cross. So we have like this. And then maybe here is S. So maybe let's look at this situation. So we assume that this cross 0, but these two don't cross. And then in this situation we defined alpha of S. This is the biggest binding number for an eigenvalue less than, for a negative eigenvalue. So in this case, alpha of S is minus 2. And then we also, because there are 2, there is a parity. So because there is these 2 siblings. And now in this example, both both of them are less than 0. So then we define the parity. This is 1. And then the Conley-Sander index, psi s, this we can take as definition in this case as is 2 alpha s plus ps. This would be in this example minus 3. And maybe let's look different examples. So if we have for pi minus 2 pi 0, 2 pi, so on. And now let's assume they cross. But from this family, one crosses, but the other one doesn't cross. Then alpha s is still minus 2 because we still have a negative eigenvalue of winding number minus 2. So alpha of s is in this case still minus 2. But now because the sibling of here crossed 0, the parity is 0. So ps is 0. And here in the Conley-Sander index is minus 4. 2 alpha s plus ps. This was end of last lecture. Is there questions to the last lecture? Good. Then now we can associate. So this we associate Conley-Sander index to a path of symplectic matrices. Now, if you have a periodic orbit, so if you have sigma three-dimensional manifold and lambda contact form and R free vector field, and then suppose we have a periodic orbit gamma from S1 to sigma periodic orbit. So we have gamma dot of t equals tau gamma at tau r gamma t bigger 0, the period. And suppose it's contractible. Periodic orbit. So if it's contractible, we have here gamma, and then we can fill in a filling disk. So for example, if this periodic orbit is the asymptotic orbit of a finite energy plane, we can just use the finite energy plane as filling disk. And so we have a gamma bar, the filling disk. So we have gamma bar, the smooth map from the disk to sigma. So this is just setting C set less than or equal 1, such that gamma bar of e to the 2 pi I t equals gamma p. And now let us look at, so we have, if you have a contact manifold, so recall we have the psi is the kernel of lambda. This is the hyperplane distribution. So in this case, if you have three-dimensional, this is a two-dimensional symplectic vector bundle over sigma. So we look at the pullback over D. So this is a symplectic vector bundle. Where the disk is just contractible, so we can trivialize. So D is contractible. So therefore there exists symplectic trivialization. Tau trivialization, so we trivialize this bundle to the trivial symplectic bundle over the tau bundle map. So that tau x from gamma bar tau z from gamma bar z to c is linear symplectic. All set D. And now, because gamma is a periodic rebar bit, so we have if we look at the differential of the flow, and if we restrict this to psi gamma 0, so this goes from psi gamma 0 to psi gamma t, and this is linear symplectic. So using the trivialization, we can now define a path of symplectic matrices. So define a path psi from 0, 1 to SL2, 2 T maps to, so we look at E phi R T tau restricted to psi gamma 0. And then we'll use the trivialization, the inverse, and then backwards. So we conjugate with the trivialization, and so we get a path of symplectic maps from C to C. And as a note, psi of 0 is the identity. And so we can associate to this psi condescender index. We can consider the condescender index of psi. And the condescender index is homotopy invariant. So homotopy invariance of condescender index, then this condescender index is independent of trivialization, tau, and depends. So we also had to choose. We had to choose a filling disk, and it depends. It depends on the filling disk up to homotopy. Depends on filling disk up to homotopy. However, if pi 2 of sigma vanishes, then all filling disks are homotopic, and this Conley-Sender index is well defined, independent of the choice of the filling disk. So conclusion, if pi to sigma is trivial, then Conley-Sender index of psi only depends on gamma. So we have, it makes sense to talk of the Conley-Sender index of periodic Reeb orbit. And so let me assume in the following that sigma is S3. So then we don't have this kind of problem. So we always have well-defined Conley-Sender index. In the following, assume sigma equals S3. So we have well-defined Conley-Sender index. And so suppose we have U tilde. U A is finite energy plane, and then we know that there exists asymptotic Reeb orbit. There exists. Yeah, now we can make some English exercise, because it's always difficult, and the. First, there exists a asymptotic Reeb orbit, because a priori it's not well defined. There might be several ones, but if it's non-degenerate, then it's the, because then it's uniquely determined. Then we can, so we have gamma, first a, n asymptotic Reeb orbit. And assume gamma non-degenerate. So that means that so if you look at the flow of the linearization of the flow of the Reeb vector field gamma 0 restricted to psi gamma 0 minus identity of gamma 0. So this is different from 0. So we don't have eigenvalue equal to 1. And then it's that. Then it's unique. Then it follows gamma is uniquely determined by utility. So we have now the asymptotic Reeb orbit. And now I want to explain the following theorem. Of Hofer, Wysotsky, and Sender. Namely, under these assumptions, the Conley-Sender index of this asymptotic Reeb orbit is bigger or equal to center of gamma is bigger or equal to 2. So you can think of this theorem as an automatic transversality result. So, so if you can ask Suguru, because Suguru is expert on this index in symplectic field theory, and so Suguru can explain to you that in these situations the virtual dimension of, if the Conley-Sander index of gamma would be less than 2, then the virtual dimension of this of the moduli space of finite energy planes would be negative. So, of course, nobody has seen a manifold of negative dimension, but it's just virtual, because there is a transversality issue. It might be not transverse, and so there might still exist solutions, also they are kind of non-generic. And in higher dimensions, this is a very difficult problem. So if you have a negative virtual dimension, this does not imply that there are no solutions, because it might be not transverse. So you have something like this, non-transverse thing. And yeah, there are many techniques. Sometimes you can just perturb almost complex structure to make it transverse, or sometimes you have to use like Koranishi structures or heavy machinery to perturb it, to make it transverse. But this means you don't need to perturb anything. So it is true for any J. You don't need to wiggle at J. So you have just any SFT like J. Remark. So the theorem is an automatic transversality result. And so what I tell you now, if you don't have heard this, then maybe Professor Ono or Suguru can explain you what this means. So if mu Conley-Sander of gamma is less than or equal 1, then the virtual dimension of moduli space of finite energy planes and actually modulo gauge. That also makes it so difficult, because we always have this gauge action. We have the direct similitudes as reparametrization, and we have the R action. So we have how much is it? Five-dimensional gauge group. So actually we have to divide out this gauge group. As a modulo gauge is modular space of finite energy. Modulo gauge is negative. But here we don't. Here we do an argument which just works in this low-dimensional case. Namely, we argue by binding number. So. Let us make some preparations for proof of the theorem. So we have T. Because of this hyperplane distribution, we have the splitting of, so if Z is in C, so we have here U is a map from C to sigma 3, and A is a map from C to R. And so if I have set in C, then the tangent space of our contact manifold splits into the hyperplane distribution plus the one-dimensional space spanned by the Reed-vector field. And we let pi is the projection from this tangent space to the hyperplane distribution, so projection along the Reed direction. Projection along the Reed direction. And we have again U star xi over C, and this is contractible. So we choose a trivialization, some complex trivialization. So choose tau from U star xi to CC complex trivialization. A bundle map such that for all set in C, tau z from xi u z to C is complex linear. And then we look at so we first look at dx of u, so the partial derivative in the x direction. So this lies in the tangent space of sigma. So then we project to the hyperplane distribution, and then we apply trivialization. So this is from C to C. Smooth map, and it's basically holomorphic, almost holomorphic, because U satisfies this holomorphic curve equation, almost holomorphic. So let me recall you some facts about binding numbers. So recall. So suppose first we have just C to C, first just smooth map, not hollow, not as a real smooth, as a real smooth. And so we think of R2 to R2. And let me abbreviate RF. This is the regular set. The set in C such that f of z is different from 0. And let's consider gamma from S1 to Rf, some continuous loop in the regular set. So we have, so up to some points, we have the regular set Rf, and then we have here gamma. And then we can consider map from S1 to S1 T. So you apply f of gamma t, but because we are in the regular set, f is not 0. So we can divide by the length. And then this is mapped from S1 to S1. And we can just look at this degree. Yes. Right. This is so we have z equals x plus I. We just take the partial derivative x direction. And so define W gamma f. This is the degree of this map from S1 to S1. So this degree has some nice properties, as of properties of degree. So it's element in Z. So it first is homotopy invariance. It's kind of jump because it takes discrete values. So it's homotopy invariance. So if gamma from S1, S1 times, so we have a homotopy parameter, 0, 1. So the only thing is important is that we always stay in the regular set. We are not allowed to cross single points of f. So if this is continuous, then so gamma 0 I abbreviate by gamma 0 and gamma 1, gamma 1, then this degree doesn't change. Gamma 0 of f equals W gamma 1 of f. Then another property is the concatenation property. So if gamma 1 is a loop in the regular set and gamma 2 is another loop in the regular set, so continuous, and suppose that they have the same starting point, so this, so that then we can concatenate them, and then we have the, we concatenate gamma 1 with gamma 2, that's concatenation, this is just this is additive. Degree is additive under concatenation. So a consequence of this property is that we can compute this degree in terms of local degrees. Consequence assume that the singular set, so the complement of the regular set, the singular set, let's go with SF. This is the points in C such that f of z is 0. So this is complement, the regular set. Suppose that this is discrete. And let's pick Z0, a point in the singular set. So now because it's discrete, we have some small neighborhood where there are no other singular points of f. So because f is discrete, follows that there exists some epsilon bigger 0 such that SF intersected with the closed epsilon ball around Z0, the Z in C such that Z is less than or equal epsilon, that this Z0 is the only singular point in this epsilon ball. There's Z0. So we have here epsilon. And now, so consider we just go around boundary of this epsilon ball, so consider gamma epsilon of Z0 S1 to now boundaries in the regular set, T goes to Z0 plus epsilon e to the 2 pi it, and then define the local binding number WZ0 of f. This is just defined as the binding number around this loop around Z0. And this is because there are no other singular points in this ball. This is independent of epsilon. You can use other epsilon. So well defined, independent of epsilon by homotopy invariance. Now let's pick a big R, bigger 0, and assume that f of r e to the 2 pi I t is never 0 for all t in S1. The r from S1 to is actually a map to the regular set of S. Ft goes to r e to the 2 pi I t. And as I said, the binding number R of f, this is the binding number along this big circle. And a consequence now of this concatenation property and homotopy invariance is that we can, also by homotopy invariance and concatenation, we have that the binding number of Rf we can express as the sum of all singular points in the R ball and the local degrees. So we have a sum of the sum of local degrees. So we have here we have our big R ball, and then we have here some singular points, and then we can look at the local degrees, and then we when we make it bigger and bigger by homotopy invariance, and we concatenate and then concatenate again, and by homotopy invariance we get this degree. Now this is now suppose this is f was just real smooth. Now if f is holomorphic, we can say more, because if f is holomorphic, then this implies that these local degrees are always positive. So assume that f from C to C is holomorphic, and assume it's not identically 0, then if f of set 0 is 0, then we have the binding number, this local binding number is always bigger or equal to 1. And let's prove this claim. So we can, without loss of generality, we can assume that set 0 is 0. Everything is translation invariant. And f is holomorphic. So we have, at least locally, we have f is given by its Taylor series. So f given by its Taylor series. So we have f of z equals sum n equals 1 to infinity a n of zn. And note that the summation starts at 1 and not 0 because f vanishes at 0. And let me abbreviate by L. This is the minimum of the first coefficient which is non-zero. So we actually start, we can start here at L. So order of vanishing. Vanishing of f at 0. So we have f of z equals sum n from L to infinity an zn. And this local degree is actually this L, this order of vanishing, namely choose epsilon bigger 0 such that the sum n from L plus 1 to infinity of an epsilon n minus L is less than or equal to L. And then abbreviate g of z. This is the sum n from L plus 1 to infinity of an zn. So I can write f of z. This is al of zl plus g of z. And g is small, so I basically can forget about g. So we have now a map from S1 to S1. T goes to al epsilon L e to the 2 pi I T L plus G epsilon e to the 2 pi I T L divided by al epsilon L e to the 2 pi I T L plus G epsilon e to the 2 pi I T L. And this map, this is homotopic, so we can homotop G away. This is homotopic to map S1 to S1. T maps to al epsilon L to the 2 pi I T L, al epsilon L e to the 2 pi I T L, which is al divided by absolute value of a e to the 2 pi I T L. And the degree of this map, this is just L. So we have the local winding number of f at 0. This is L, this order of vanishing, and this is bigger or equal 1. So this has now some interesting consequence. So this is the positivity of winding. So suppose we have f from C to C holomorphic. And we have R bigger 0 such that f of R e to the 2 pi I t is different from 0 for all t in S1. Then, because we can express the binding of R in terms of this local winding number, and they are all non-negative, the winding number is non-negative. And we can say more, namely, when it is 0, it can be 0 only if there are no singular points at all. Then it follows that WR of T is bigger or equal to 0, and it is 0 if and only if f of z is different from 0 for all z in the R around 0. So you can, if it's holomorphic, you can by looking at the big circle, you can see if there are singular points inside or not. And so as a matter of fact, so our map we are interested in, also this, we apply this to the map C to C, Z maps to EXU pi tau, and this is not quite holomorphic, but it's almost holomorphic, and there is so-called Kalemann similarity principle. So using Kalemann similarity principle, you can show that for a map like this, which is basically holomorphic, you also have this positivity of binding. This is almost holomorphic, and so by this Kalemann similarity principle, you can think of it as a holomorphic map. So by Kalemann similarity principle, this positive of binding holds for the positivity. Okay, is this clear or other questions? Good. Then so that's the first ingredient in the proof of this theorem, this positivity of binding. Then there is a second ingredient, which is the asymptotic behavior of a finite energy plane, asymptotic behavior of a finite energy plane. So it roughly says following. So if we have tilde UA finite energy plane, and if we have, and gamma is non-degenerate asymptotic orbit, Reeve orbit, then asymptotically it exponentially converges to this asymptotic ring-orbit, and it converges like an eigenvector. So here we have this asymptotic, we have the operator. So we have A gamma, this asymptotic operator, and then we have then there exists eta in an eigenvalue, which is so a negative. So we have a negative eigenvalue. And xi eigenvector to eigenvalue eta, so such that, and maybe after reparameterization, u tilde of e to the 2 pi s plus I t, and here I write a bit like this because this is true is up to error which also everything already exponentially decays, but the error decays more exponentially. So this we are already close to this asymptotic orbit, and we make some error which is even much more smaller. So this is basically, the u is basically exp gamma t e to the eta s xi t, and so tau is a period of gamma. So the A asymptotically goes like tau s, tau the period, and the u goes basically like this eigenvector which decays exponentially. Or eta is negative. So this gives, if s goes to plus infinity, this goes extremely fast to minus infinity, and the error decays even faster, also exponentially, with all derivatives, even faster. So this is up to error of faster exponential decay. And exponential map here is with respect, so we have the metric, or we have omega, we have j, this gives a Riemann metric, and so we have exponential map for this. And this is, so yeah, this kind of, one can state quite precisely what's going on, but it's actually not so important what's going on here, because everything we do is up to homotopy, and so you can this error, you don't see it in the homotopy. So this here is irrelevant in homotopies. In homotopies. Yeah, and this exponential. So this is, many people worked on this exponential decay. So Hofer, Wysotsky, Sender, they had some first version, but then many PhD students of Helmut had to work on this, and most of them disappeared this was starting with Hofer, Wysotsky, Sender. then Helmut had some, so Kriener, when I was actually a student at ETH, he was assistant, and then Mora, but the day after that, I think they didn't stay in mathematics, and then the one who survived is Siefring. So you have this behavior, and now because of this behavior of this now up to this error, which we don't need to worry about in homotopies, we can where is it? This here, we want to compute this, and now we have a different way to compute it. We can also compute it because this eta now also has a winding number. This is what we did. On Monday. We associated to the eigenvalue a winding number, so we can relate this the winding number of this for big R with the winding number of eta. So, because here we have e to the pi s. So here we have make little bits we have to think, because here we look at the partial derivative with respect to x, but here if we take the partial derivative with respect to the radial direction, then we have the winding of this corresponds to the to the winding of psi. But by definition, this is the winding of eta, because psi is an eigenvector to the eigenvalue eta. Yes, yeah, you're right. Yeah, right. So that's how they link. Yeah. Yes. So consequence. So we have the winding number of tau pi dr. So here is now we take the derivative like this, the radial derivative, not the x derivative. This is equals w of eta. And now we just need to see how the winding number, if we have here dxu and here dru, how they are related for R large enough. So how are WR PR of U and WR tau pi x of U related? Yeah.
Tau is the reflection, right?
No, this is A. This is in R. Huh? So this is in sigma,
Oh.
and this is in R.
And then these R coordinates have tau, the period A, right?
Tau times S. So it goes to infinity.
Then not S, but tau S, right?
Yeah, the period scales a bit how fast you go. But tau is positive. Okay.
He uses gamma in this parameterization. Gamma is just L.1.
Yeah, right. This is what I use the convention gamma dot of t equals tau r gamma t, so that gamma has period 1, and then tau corresponds to speed. But you can, if you reparameterize it, you can, if you make the speed the revector field, then it becomes the period. Okay. Other questions? So note, we can also write this a bit as if we have tau pi dxu, we can also write this a bit more fancy as tau trivialization pi. Then we apply the differential du to the vector dx. And we have tau pi dru. Can think of, we apply t pi du to dr. And this here is linear map, composition of 3 linear map. And so in general, if A is smooth loop of invertible 2 times 2 matrices, two matrices, and we have V1, V2 smooth maps to R2 complement of 0, then the degree of the map T goes to AT B2T divided by AT B2T norm equals the degree of T AT B1T norm A to B1T plus the binding of V1, 2, and so we have the binding of V1, 2. So we have here circle. Then so I have V1 of T, V2 of T, then I don't know what they do, whether they one point like this. And then at one point they might become parallel. And so. And so in particular, if we do this for the dx and dr, so if you have the binding of dx dr, then you see as a this case here we have dx dr, here they are parallel. Then here as a dx always points in this direction, dr points here above. Then here they become negatively parallel. Like this, here is dr, and so we have this is 1. So we have the relation that wr of tau pi dru, this equals the binding of tau pi dxu plus the binding of dx dr. This here is 1, and this here is bigger or equal 0 by positivity of binding, because this is almost holomorphic. This is by positivity of binding. So conclusion is this this binding number is bigger or equal 1, and this is the binding number. Maybe it disappeared of eta of this. And so also follows that 1, this is less than or equal wr tau pi dru, and this is w eta, where eta is the asymptotic eigenvalue, and this is negative. This is, we all know that eta is negative. So this is the asymptotic eigenvalue. And now the theorem is basically proved. As a proof of the theorem, as a recall theorem, as a proof of theorem, we want to prove that the Conley-Sandler index of the asymptotic orbit is bigger or equal 2. And we have the Conley-Sandler index of gamma. This is 2 times alpha plus p. And alpha is the maximum of the binding number, so that eta is a negative eigenvalue. And the parity, this is either 0 or 1. And now, by this formula, we found one eta, which is negative, and has winding number bigger or equal 1. So we conclude that alpha is bigger or equal 1. So with star, it follows that W eta, this is that alpha is bigger or equal 1, and therefore the Conley-Sender index of gamma, this is 2 alpha plus p, but p is 0 or 1, so this is bigger or equal 2 alpha, so this is bigger or equal 2. That's the theorem. Okay. And we actually can, the proof reveals with other interesting properties. Namely, what we can say is if the Conley-Sender index is of the asymptotic orbit is less than or equal 3, the U, also the sigma part of the finite energy plane, has to be immersed and transverse to the Reeb direction. So maybe corollary is a corollary of the proof, not of the theorem. Assume U tilde as U alpha from C to sigma times R is a finite energy plane with non-degenerate asymptotic Reeb orbit gamma such that Conley-Sender index of gamma is less than or equal 3. Then it follows that U is immersed and R is transverse to the image of U. Maybe as a remark, so for this non-degeneracy, we also need, this is also quite crucial for this asymptotic behavior. It should continue to hold if you have kind of more spot situation. For example, in the only example only explicit example I gave you for the standard sphere in in C2, there it was not non-degenerate, but it was more spot. And so you also have this asymptotic behavior. But yeah, there are very degenerate situations where this can fail. Good. So let's prove corollary, and so we have 3. This is by assumption bigger or equal the Colny-Sendra index of gamma, and this is 2 alpha plus p, and this is also bigger or equal to, yeah, this we now know by the theorem. But p, the parity, is in 0 or 1, so that means alpha has to be 1. Is 1. And so if eta is in the spectrum of the asymptotic, if you have any eigenvalue in the spectrum of the asymptotic operator which is negative, then its winding number has to be less than or equal 1. Then by definition of alpha, because alpha is 1, we have the winding number eta is equal 1. So that means the winding number of the asymptotic eigenvalue is less than or equal 1. Asymptotic eigenvalue is always negative. So consequence, also if eta is asymptotic eigenvalue, so just remind us, with asymptotic eigenvalue, I always mean that we have this u tilde e to the 2 pi s plus it is x gamma e eta s xi tau s. So this eta, I mean, this asymptotic eigenvalue. Under this eta. Then, yeah, then of course it also this, because this is negative, it has to be less than or equal 1. So it follows w eta is less than or equal 1. But we also know that what we have seen in the proof of the theorem So my proof of the theorem has shown us that 1 is less than or equal the winding number of tau pi dru, which is the winding number for big R, winding number of eta. This is less than or equal 1. So we conclude that it's 1. It has to be 1. So it follows that WR tau pi dru is 1. And as we just discussed before, also again, proof of theorem, we had WR of tau pi dx u. This is equals WR tau pi dru minus 1. So this in this case has to be 0. But by positivity of winding, this means this has no zeros. So positivity of winding, we have tau pi dx u z is different from 0 for all z in C. But tau here was just trivialization, so we can, this is just linear bijection, so we can forget about tau. So actually pi dxu is always different from 0. So it follows that pi dxu z is different from 0 for all z in C. And you remember pi was the projection from the tangent space to the hyperplane distribution along the Rie vector field. And but U, we also know U is holomorphic. U is holomorphic for this SFT-like, almost complex structure. So we have we get the equation pi dxu plus j pi dyu. This is 0. So in particular, if dxu is never 0, then dyu also is never 0. So it follows that pi dyu, which is just j pi dxu, is different from 0 for all z in C. So we have p and additionally p dxu and p dyu, they are linearly independent. For all z. See? So this du of z, this was this goes from t z c to xi u z. This we can identify with c. This is also bijective. And in particular, start here. Star. So we have no. This is a bijection. Then we have that du z this is still pi du of z is a bijection. So now du of z, this goes from t z c to tu z of sigma. This is injective, and so it's an immersion. So we get u is an immersion, and because of star and the fact that TUZ is just splits the hyperplane plus the span of the refractor field, we have R is a transverse to the image of U. That proves the corollary. And now, Hrnewitz, he introduced the notion of fast finite energy plane. And in the following, we want to concentrate on fast finite energy plane. So you can make a very easy definition, but then you don't understand so well why he calls them fast, but you will understand them why they are called fast if you know about this asymptotic behavior and the winding number of eigenvalues. So the one way to define fast finite energy plane is the following. So finite energy plane tilde UA from C to sigma times R is called fast. Okay, so we should always have non-degenerate asymptotic with non-degenerate asymptotic big orbit. Is called fast. Now we can just define it so that in this way, so that if U from C to sigma is an immersion such that the refractor field is transverse to the image of U. And so why he calls them fast? As a reason for this terminology so if eta is the asymptotic eigenvalue, then we have W eta, this equals WR of pi dRu. This is bigger or equal 1, or R large enough. And moreover, by the definition of the Condensender index, we get that 1 is, so this asymptotic winding number of the eigenvalue, the winding number of this asymptotic eigenvalue is less than or equal the Condensender index of gamma half, and you take integer part. So we have R, this is the maximum n in Z, n less than or equal R, for R in R, integer part. And by the monotonicity of the winding number, we know that if eta prime are eigenvalues such that eta is less than or equal eta prime, then we have the winding number of eta is less than or equal to the winding number of eta prime. So therefore, U fast means that if U is fast, we can also rephrase it that if U is fast, this has to be actually 1. If U is embedded, U is in immersion, then by what we discussed, the asymptotic winding number has to be 1. So that means it's as small as possible. So if you look at the general asymptotic eigenvalue of any finite energy plane, not necessarily fast, you just know that this asymptotic eigenvalue lies between 1 and integer part of half the Condensender index. But if it's immersed transverse to the image of U, then by this positivity of winding number, this has to be 1. And this means this is the smallest possible winding number. And because of this monotonicity, this means it decays as fast as possible. If this is small, then you have the decay is like eta s, and this is negative. So this is very negative. So you have very fast decay. So that's why he calls them fast. That means that they are decaying. In this model, you can look at the moduli space of all finite energy planes to the given asymptotic orbit, and they all have some asymptotic eigenvalue somewhere here. But as smaller this, because of this monotonicity, as smaller the winding number is, the faster is their exponential decay. And if we have an immersion transverse to U, this has to be 1. So by so this discussion is asymptotic eigenvalue of any finite energy plane, not necessarily fast one. Here. is asymptotic eigenvalue of any finite energy plane tilde asymptotic to gamma, then this, and if U tilde is fast, then by the discussion in proof of theorem, the binding number of delta is 1. So it's smallest possible, i.e. Exponentially asymptotically U tilde converges as fast as possible. So that, and so Hirnwitz had the idea so that instead of, if one is interested in finding global surface of section, then you don't want a too big moduli space. So what you would like to produce is just this picture. You would just have some S1 family. And if you look at the moduli space of all finite energy planes asymptotic to gamma, this might be a very big space. So now you look at the subspace just of the fast ones, which you can interpret as the one which have this asymptotic binding number equals to 1, and this is a much smaller moduli space. This is actually this is the condensation index of gamma is bigger or equal 3. Then this is modulo gauge is always one-dimensional manifold, and so that was his insight to not to look. In order to find global surface of section, you don't look at the whole moduli space of all finite energy planes, but just on the subspace of fast ones. Good. So maybe I have 15 minutes. So we will, as I start little, and then we'll continue in the afternoon. So I would like now to discuss next the intersection property of fast finite energy planes.
Let me make sure that so if my finite energy plane is fast, then the specific periodic orbit and horizontal index 2 or 3.
Always, not. Otherwise, you don't have.
Yeah. So yeah, the discussion we had is that implies that.
So if the Colny-Sender index, right? If the Colny-Sender index is 2 or 3, then everyone is automatically fast.
And then is fast implies also the reverse?
No, so you can also have a periodic orbit of bigger Colny-Sender index.
With fast.
But then you have not what you see here. yeah, right. If it's 2 or 3, then this is 1. But maybe if it's more, then you can also have other finite energy planes, which have asymptotic so that is bigger one. So they are not necessarily immersed.
Okay.
So if that's good. So make this remark. So if mu Conley-Sender index of gamma is 2 or 3, then any finite energy plane asymptotic to gamma is automatically fast. Any finite energy plane asymptotic to gamma is fast. That was also the corollary. But what was the insight of Hrnewitz? Also, even if the Conley-Sender index of gamma is bigger, 3, then at first it looks this moduli space of finite energy planes doesn't look good to find global surface of section because there are much too many. It's much too big. But if you restrict yourself to the fast ones, and this is also natural because if you want to have a global surface of section, it should be actually embedded, not just immersed, but then it definitely should be immersed. So then then you just look at the subspace of them which have whose asymptotic orbit has winding number 1. So that enabled him also to construct global surface of sections for periodic orbits which have Conley-Sender index bigger than 3. Okay. Sorry? Yeah, right. So this takes just it takes numbers here in. It takes numbers between 1 and the integer part of half the Conley-Sender index.
That is for W.
Yes. Right. So right. We can write. So we have mu gamma. This is the moduli space. Moduli space of finite energy planes asymptotic to gamma, and now we have we have W 2 1 mu Conley-Sender 2 to this interval, and namely we take here U tilde A and map it to. So actually this maybe I should write eta U. It depends actually just on U, not on the R direction. So this is the asymptotic eigenvalue of U, and then the fast ones are the preimage of 1. So we have right. Yes, it's yeah. Yes, the fast ones they are extremely nice because you also have this automatic transversality, which I explained some part of it. You always have for the fast ones. For the other ones, this moduli space, the whole one does not need to be a manifold, but the fast ones they are. So this is also for my purpose, I would ignore the other part. I just consider the fast part. But if you have other, if you want to do other things, yeah, maybe, yeah. So we have, but now m fast of gamma. This we can take a inverse 1. This is. So, actually, we'll do this in the afternoon, well, maybe just me. So, as a Siefring's intersection theory for, and so he actually has an intersection theory for all of them, not just the fast ones. But what I will explain is just for the fast one. Since there is somehow for I think the most powerful applications is for the fast ones. Section theory for fast finite energy planes. And maybe let me just indicate a bit what we are doing this afternoon. So, what is a strong feature of the intersection of holomorphic curves is that they have positivity of intersection. Also, holomorphic curves. This is this. And here we need dimension 4. So there is nothing in higher dimensions. Yeah, so we have 2-dimensional curves in a 4-dimensional target. They intersect isolated points in 4-dimensional target spaces. They have a positivity of intersection. So it's like this binding. So if they intersect, then they always intersect positively. So if their intersection number is 0, they don't intersect at all. That's some good application. But our holomorphic planes, they have a bit nasty property because they have non-compact domain. So and then the problem with holomorphic planes so we have a C. This is we have a non-compact domain, and then so if we have 2 holomorphic planes. So they intersect, and then asymptotically, of course, my picture is always a bit misses some dimension. So you can think now there's 2 planes, but if they go to have the same asymptotics, then asymptotically then you don't know. So maybe might have some asymptotic intersection here, and so then it's not clear that intersection number is homotopy invariant. So So also intersection points at infinity and this is a problem with homotop invariance. Now, what Seifring does, he perturbs a bit, so he makes asymptotic different. Then he gets homotop invariance, but then because he perturbs, it's not holomorphic anymore everywhere. And so what we have to discuss is how you perturb them, but you still want to keep positivity of intersection. And that's kind of subtle theory, and it's very much uses again this asymptotic eigenvalues, eigenvectors. So these asymptotic winding numbers. So idea perturb at infinity. So we have this, but now we perturb this. So we go here somewhere else. So then we have no asymptotic intersection. And then we have homotop invariance. And this is somehow the problem which Seifring solve is want to keep positivity of intersection. So that's the plan for this afternoon, and I think now it's 12. So are there questions? So then, yeah.
Did we use topology of three-dimensional sphere except for the balancing of?
So far we just used it to have a well-defined Conley-Sender index. These theorems hold a bit more generality, but then it makes a bit nasty to write them down because otherwise the Conley-Sender index depends on the filling disk. But we actually have filling disk because we have the finite energy plane. So you could just define it with respect to this finite energy plane, and then otherwise we didn't use otherwise so far. But actually in the restricted C-body problem we also will get S3, and so this for me no bad assumption. So I like actually this assumption that we are just working for S3. Questions? So then we continue at 1:30. Right, yeah.